So for us, the definition of a sequence is going to be this. It's going to be a function. It's weird, right, that there was a function in there. A function whose domain is the positive set of integers. And I'll give you an example like this, okay? Okay, so for us, a definition of a sequence is a function whose domain is the positive set of integers. That's the way we're going to represent the positive set of integers. Now, what is an integer before we even go on? What's an integer? Is 1.7 an integer? No. 1.7 is not an integer. We're talking about whole numbers, but not the number 0. Good. So 1, 2, 3, 4, 5, 6, 7. Okay? Now a sequence, let me give you an example of a sequence here, and then we'll start talking about it, right? So here is a sequence. 1, 1/2, 1/4, 1/8. What will be the next one, you guys? 1/16, and then you're going to see this dot, dot, dot. All right, no, very good. Those are not integers, okay? But that's not, I'm going to point this out to you. So what you see is a sequence of numbers. It's 1, 1/2, 1/4, 1/8, 1/16. But the definition says it's a function whose domain is a positive integer. So what are they talking about? They're talking about this down here. You got to look down below. Now, I always draw, what color do I use? I always draw these little lines in there to separate my sequences out. The book might not do that. The book might use commas. The reason I do is because below it, I write this. A sub 1, A sub 2, A sub 3, A sub 4, A sub 5. Now, do you see where the domain is? Do you see where the integers are? No. Okay, they are right here. So when we're talking about the domain, we're talking about these subscript numbers down here, all right? This is what we're talking about. Those are the domains. Those are the inputs. The outputs are the actual numbers up top, okay? So these numbers up top here, the 1/8, the 1/16, all of that right there, these have a name. We call these the terms. The terms of the sequence. Okay? So we could say the second term is 1/2. The third term is 1/4. The fifth term is what, everybody? What's the fifth term of the sequence? 1/16. Very good. So in terms of it being a function, what you got to ask yourself is, okay, if I input a 1, the output is a 1. If I input a 2, the output is a 1/2. If I input a 3, the output is a 1/4. And so on and so forth. That's why it's called a function, okay? Then you'll see this dot, dot, dot on the end of your sequence. What do you think the dot, dot, dot means for the sequence? It means it follows the same pattern. Keep going in that direction, okay? Then eventually you're going to come up against this, the a sub nth term. Ooh. So what we're doing is we're moving from the concrete to the abstract, right? Okay, we see this concrete example of a sequence. We have 1, 1/2, 1/4, 1/8, 1/16. How do we generalize that sequence into a pattern that we can involve ends, okay? So this is what I want you to think about right now. So the question is, how would I describe the nth term? What would I place here to describe all of those? So we just noticed that we're trying to figure this out, and we noticed that the numerator of these is all 1. So let's start with that, okay? So it's going to be 1 over something, okay? Now, what do you notice about this denominator here? What is this denominator? This is 2. Then this is what? 4. Then this is what? 8. Then this is 16, right? So all of the denominators are multiples of 2, but they're also powers of what? 2. Also powers of 2, right? What's 2 to the 0 power? 1. What's 2 to the first power?
2.
What's 2 to the second power? 4. What's 2 to the third power? 8. What's 2 to the fourth power? Okay, now, here's what your brain has to ask yourself. Your brain has to ask yourself, okay, if I put in a 1, I need to get an output of what? 1. This is where the function part comes in. If I put in a 2, I need an output of what? If I put in a 3, the output needs to be, if I put in a 4, the output needs to be, okay, so how do we get that to work out? What do you think, Bobby? Do you see it?
Yeah, 1 over 2 to the n minus 1.
You are 100% correct. 1 over 2 to the n minus 1. This is how we would describe the nth term in the sequence. And let me explain how. So let's take, for example, let's take the 4th term, okay? If I plug in a 4, I get 1 over 2 to the 4 minus 1, which is 1 over 2 cubed, which is the 1/8. That's how we got that 1/8 there, okay? So we're going to be good at coming up with the nth term of the sequence. But I wanted to give you kind of an overview of what sequences are. Okay, here's an example. Let's practice one. This one's a little bit easier. Karen, what's the 2nd term of the sequence? 10. Good. What's the 4th term of the sequence, everybody? 20. Very good. Okay, I'm asking for the nth term of the sequence. So your job here, your job is to somehow find a relationship between the input of 1 and the output of 5, the input of 2 and the output of 10, the input of 3, output of 15. Does anybody see a relationship there? Yes, what do you see?
That if you multiply each one by 5.
You multiply what by 5? Yeah, Ryan, what did they multiply with what?
The integer.
Yeah, the inputs, the domains, right? The n value. So a sub n is going to be nothing more than 5n. And that's how we would describe it. Does that sound fair? Is that fair enough? Now, when we're talking with sequences, you're going to see these sideways mustache brackets. And whenever you see an a sub n written like this, you know you're going to be talking about a sequence. So that's another way that you're going to see it described to you. So when you see those sideways curly brackets, you're talking about some sort of a sequence there. All right, so we're going to write the first 5 terms of this sequence here. A sub n equals n minus 1 over n. So I always like to lay out my sequence in terms of what I've been given. Here's a sub 1, here's a sub 2, a sub 3, a sub 4, a sub 5. Okay? So now how do I get the first term? What do I do? Remember, it's a function, so I need an input to get an output. Yes?
You plug in the 1.
You're exactly right. You plug in the 1. So what would 1 minus 1 over 1 be? It'd be 0 over 1. So my first term of this sequence should be 0. What should my second term be? 2 minus 1 divided by 2. 1/2. Very good. Okay. What should my third term be? 2/3. Very good. Now, does anyone see a pattern? Yeah. So what's the next one going to be? 3/4. And the next one finally? 4/5. So do you see what I mean by students who can see patterns really well? You tend to pick this up pretty good. All right, please take your calculators out. So our calculators do have the ability to produce the same sequences that we've just done. So it's a good way to check our work and use it for future reference. So here's what we're going to do. My calculator is a TI-83, so the inputs are going to be slightly different than anybody who has a newer calculator, but it essentially does the same thing. So follow along with me here. So I'd like you to push second, and I'd like you to push stat, which is this button over here. Stat, second stat. And then you should see a screen that says names, ops, and math. We're going to move over to ops. And then if you go down to option number 5, notice it says SEQ. That stands for sequence. Okay? So you can either push button number 5 or you can either scroll down number 5, push enter. So now, this is what I see, but many of you probably see something that says what's it say, Bobby? Expert, variable, blah, blah, blah. Okay. Start and end. Okay, good. So here's what we're going to put in. For the expression, EXP stands for the expression. We're going to put in this expression, n minus 1 over n. Except we're going to use x's because our calculator has the variable x. Now, the numerator must be in parentheses. So put a parenthesis, go x minus 1, close it, divided by x. Okay? That's the expression. This is what it's talking about for EXP. That's the expression. Now, for you guys who have the fancier calculators, all you got to do is move down to the next line. For me, I use a comma. All right? Yeah, and the parentheses. No, I don't for this one. No. Okay. The next thing is we're going to punch in, okay, the variable that we're going to use. So that for the variable is going to be x. So we just put x. Go on to the next line. Then it says start and end, right? Well, we're starting with the input of, check it out, 1, right? Down here, my domain value is 1. What's my end value? 5. So I'm going to go 1, comma. You guys move down, go to 5, comma. Now, step. What is the difference between the first and second inputs? It's the step of 1. Usually we go in order, right? I go up 1 at a time. A sub 1, A sub 2, which means I'm just counting the sequence by ones. I'm not counting every fourth term of the sequence, right? So the step should be 1. Okay? Then I close my brackets, and then I push enter. Oops. I probably don't need that extra one. I don't.
It actually just puts it in.
Now for you guys, when you do paste, it automatically does what I just did into your calculator, right? Now notice the calculator gave us this, but we want fractions. So of course we can hit the math button, go frac, enter again, and bam. The calculator then produces the same sequence of numbers that we produced given by this expression. Okay, so what I would like you to do in your groups right now, this is pretty much a you try. What I'd like you to do is come up with a way to represent the sequence. So basically find the nth term, find a way to represent the sequence that's been given to you here. Now remember, this is a sub 1, a sub 2, a sub 3, a sub 4, and they're all the same. A1, a sub 2, a sub 3, a sub 4, a sub 1, a sub 2, a sub 3, a sub 4. And then this one, I haven't given to you yet. We'll save that one for a second. And then a sub 4. Okay, right now. The first one. Amy, what'd you get for the first one? Yeah, that one's pretty straightforward, right? The nth term, a sub n, is just representative of 2n. No big deal, right? That's how we represent even numbers, right? 2 times whatever will always be an even number. Okay, what about the third one there?
Oh, I had it written.
A sub n, what would it be? Anybody?
2 and
2n minus 1. That's how we represent odd numbers, right? Double it, then subtract 1. You've got to be at an odd number no matter where you are. Okay, third one, a little bit more challenging. I'm going to ask Theo since he got it first. Theo, what'd you go with for part C?
1 over 3 to the n minus 1.
Good. 1 over 3 to the n minus 1. Very good. That's the correct answer. 1 over 3 to the n minus 1. Some students see this, 3 to the negative n minus 1. But we represent exponents as positive. So notice that would be the same thing as 1 over 3 to the n minus 1, which is exactly what we have. Okay, for D, I'm going to give you the way that we define it. I would like you to write the first 4 terms. Actually, I'd like you to write the first 5 terms. No, I'd like you to do it by hand, okay? So give me the first 5 terms of this sequence and put it there for me. Here we go. Let's talk about it. What did you guys get for the first term? I got a negative 1/3. Second term, what'd you get? 1/5. Third term, what'd you get? Negative 1/7. Next term? 1/9. Next term? Okay, what's special about this particular sequence? What do you notice? The signs are changing. That's why I gave you this one special, okay? And this part right here is going to determine a sign change or an alternating sign between the sequence. So whenever you see a negative 1 to the n, okay, in general, you can expect to have an alternating signed sequence, okay? So I wanted to make sure that you're aware of that and make sure you saw at least one of those. All right, we're going to talk about the factorial symbol, which I'm sure you have seen before. This does not say, n, like super excited n with an exclamation point. It looks like an exclamation point. It's not, though. It's a factorial symbol. So what do you already know about factorials? Anybody know what factorial means? Yeah, what do you think, Claire?
It's like that number and it descends.
It descends, but do we add them? Do we divide them? What do we do? We multiply them. So what would 3 factorial be, you guys?
1 over
3 times 2 times 1, which would be how much? It would be 6. What about 4 factorial? What would that be?
4 times
4 times 3 times 2 times 1, which would be 24. What about 5 factorial? What would that be? It would just be 5 times 4 factorial, right?
Yeah.
120.
That would be 120. Yeah, very good. Okay, now, how do I represent the general? So we have some concrete examples. How do we go to the general? What would n factorial be? How do I write that out? So we would start with what? N. And then what would the next term be?
Minus 1.
Yeah, there you go. Times n minus 1. What would the next one be?
Times n minus 2.
Times n minus 2. And then when do we stop?
Times never.
Until, no, we do stop somewhere. When we get to what?
Well,
Not 0. Because if it was a 0, we'd cancel everything out, right?
Oh, yeah.
Yeah, so instead we stop at 1, right? So that factorial symbol stops at 1. We have a couple of special cases, everybody, that I want to talk to you about, but I want you to discover them on your own. Calculator. And here we go. I'm going to show you where this button is on your calculator. So let's test, let's do 5 factorial on the calculator. We hit 5. Then, underneath the math button, click the math button here on the left-hand side, the math button. And notice at the top you have 4 tabs: math, num, CPX, PBR. You're going to go over, sorry, I always see peanut butter and jelly sandwich, but that's not what that is. Okay? It's PRB, sorry. Go over to the right, that one. It stands for probability. Anyways, go down to option 4, and look, there's your factorial symbol. And by pushing enter, of course, you get 120, which is what we came up with here. Ladies and gentlemen, before you push the button, okay, take your best guess. What do you think 0 factorial is going to be? Before you push the button, what's 0 factorial? Take a guess. So you should have discovered here that 0 factorial is 1. That is pure definition for us today, all right? So some special cases, 0 factorial is a value of 1. So 1 factorial is also a value of 1. So we have some special cases for us today. The reason being, when we start doing some probability counting, if 0 factorial was anything other than 1, we would not be able to calculate some probabilities that we need to be able to do later on down the road in section 8.6. So for us, pure definition. Okay, let's move on and talk about the 6th thing called recursive formulas. So here's my own personal definition. We have to know something about the previous term in order to get the next term in the sequence. That's what recursive formulas basically mean. We have to know something about the one. Let me give you the most famous recursive sequence in history, okay? The first term is a 1. The second term is also a 1. The third term is a 2. The fourth term is a 3. The fifth term is a 5. What is the 6th term of this very famous sequence? It's an 8. Very good. What's the 7th term? Okay, what are you doing? What are you doing?
Adding the 2 before together.
Okay, so let me show you how this fits into my definition. In order to get this term, I had to know something about the previous ones, right? So there's no real way, if I asked you, hey, what is the 127th term of this sequence? What would you need to know?
The 125th.
The 125th and 126th. That's recursive. It builds on itself, right? So you have to know something about the previous term. Anybody know the name of this sequence? It's a Fibonacci sequence. It's the most famous recursive sequence that we have. Okay? Shows up all the time, has all kinds of fun applications, and it is in nature. Yes, very, very good. Okay. All right, so here's an example. The first term is 1, and then you have this this over here, this definition in this box here. So let's do a little side note for you, okay? Let's say I have 3 numbers, okay? If I know that this is the nth term, a sub n, how do I describe this one, the one after it? How would I use subscripts to describe that one?
A n plus 1.
A sub n plus 1. What about this one here? A sub n minus 1. Now, let's go back and read this, okay? It says that the current term is equal to 4 times the value of the previous term. See that? That's what this says. That's the skill I want you to have. You need to be able to look at that inside that box and understand the meaning behind it, okay? So we now know the first term was given to us as 1. The first term is 1. The second term is going to be 4 times the previous term. So that has to be a 4.
So the first term will always be given.
Given to, yes. The third term will be 4 times the previous term. So it'll be what?
16.
16. The fourth term will be 4 times the previous term, which will be 64. This is a recursive formula. It's based on the one before it, or a couple of the ones before it. That's a recursive formula. All right? Okay, here's what I like you to do. I'll give you two examples here, A and B, so split it on the page here. In example A, I've given you the first two terms. This one should look familiar. In example B, I've given you the first term, and then I want to see what you come up with for the rest of them after that, okay? So talk about with your group. Take like 1 minute to work. All right, what did you guys get for part A? What did you get for part A? Yeah, well, the first ones were given to us, 1, and then 1. Okay, then what? Is that as far as we got? And then 2. And then 3 and 5. So this is nothing more than the Fibonacci sequence. So you have to realize, right, the two terms down the line is equal to the sum of the previous two terms. That's what that says. All right? That's what that says. So this says that this A sub n, if you think about it, this is A sub n, right? What's the next term? A sub n plus 1. What's the next term? A sub n plus 2. It says that that term is equal to the sum of the previous two terms. That's what that means right there. Okay? Now, the part B, a little bit more challenging. Anybody get it? What did you get, Grant?
It's 1.
Yep, that was given to you.
Yeah, and then 2.
And then 2, 6,
24.
24, and 120. Where have we seen these before, you guys?
Factorial.
These are the factorials, okay? Now, how did you get the 1, 2, 6, 24, 120? What did you see? Because not everybody sees that. What did you do?
Well,
Let me explain what he's saying. Let's take, for example, do you guys agree that the number 2 is the same thing as, what if I rewrote this as A sub 1 plus 1? Is that cool? Can I do that? What about the number 3? Is that the same thing as A sub 2 plus 1? Is that true? Well, the number 4, is that the same A sub 3 plus 1? Is that right? So notice I am writing each of these with a plus 1 on the end to match this plus 1 right there. You see that? So that means that this n here has to match that n there, has to match that n there. All those n's are the same. So, for example, to get the second term here, I notice that n is equal to a 1. So it's going to be 1 plus 1 times the value of the previous term, which happens to be a 1. So 2 times 1, there we go. That's how we get the 2. What about this one here? I would take a value of n being 2, so I'd go 2 plus 1 times the previous term, which is a value of 2. Notice I get 3 times 2, and that's where my 6 comes from. Does that make sense, you guys? Okay. So summation notation, one of my favorite things. The main difference between a sequence and a series is that a series is when we start adding these things up. So if we have a sequence and we start adding them up, we're talking about a series in that case. So for us, this symbol is going to be all over the book. When you see this symbol, and has anyone ever seen this symbol before? Yeah, at colleges, Greek life, right, and all those. So it is a uppercase E for the Greek letter in the Greek letter alphabet E. What's its name? Sigma. Very good.
It's actually S sound.
Yeah, it is an S sound. So when you see this, when your brain sees this is what I want your brain to think about. When you see this, you're gonna add stuff up. Okay? Whenever you see this, you're gonna think what, you guys? Add stuff up. That's what that means. So you see that, boom, add stuff up. Now, there are 3 things you need to know in order to add anything. You need to know where you start, where you end, and how you do it. For example, I could say, Bobby, add up all the even numbers from 12 to 56. A start, an end, and a how. Okay, that would be terrible, but you can still do it, right? So you need a start, an end, and a how. Same thing for this symbol. It will give you the start, the end, and the how. So down below is where you start. For example, it'll say like K is going to be 1. This is where you start. And then we'll go to N. This is where you end. And then this is going to be A sub K. This is going to be the how. Okay? So you have a start, an end, and a how. It'll make more sense when I show you an example. But these are all the basic parts or the components of summation notation. The big E means add stuff up. And you have to know the 3 things and how to do it. Where do you start? Where do you end? And how do you want me to add things up? So here's an example.
1 would be the starting number.
You got it. Let's say, check one. What if I say, give me the summation of the series, K goes from 1 to 5 of 3K. Now, me as your math teacher, it's important that you understand what you're looking at. You have to be able to read that notation and make meaning from it. That's the mathematics part, okay? So, okay, this wants me to add up all the numbers from 1 to 5 multiplied by 3. So here's what this looks like. When you actually write this out, this looks like this. 3 times a 1 plus, since I'm adding stuff up, 3 times a 2 plus, since I'm adding stuff up, 3 times a 3. Hey, when do I stop, you guys? Once I get to 5. It's a good thing it told me where to stop, right? Plus a 3 times a 4 plus a 3 times a 5. So from your factoring powers, you realize that that's just 3 times the quantity. 1 plus 2 plus 3 plus 4 plus 5. Which, of course, is 3 times what? Oh, 15, yeah? Which gives us what? 45, okay? So this right here, you guys, is a fancy way of saying the number 45. It's the sum of the series, and this would be a finite series because it ends. If it was an infinite series, then that 5 would be an infinite sign, okay? All right, there you go, ladies and gentlemen.